One of the things we embark on is to understand fundamentally how does dissolved iron interact with solid phase iron from a laboratory scale, and we could then extend this to a field scale. And one of the techniques we have employed is a technique called a calorimeter or calorimetry, which is just the study of heats of reactions. One of the things you could keep in mind while I make my way through the slides is that each chemical or biological reaction has a heat signature. If we could measure the heat, we could tell the reaction. And that's kind of the integral part of what we do to go along to kind of unravel some of these reactions. So this here, conceptually, this is what we call a batch calorimeter. And one could see if there's a beaker and there's water and you're able to measure the temperature over time, say short periods of time, it will be constant. All right? What if we add some solid to this beaker, force the temperature to change? So let's say we add ammonium nitrate. All right? Just drop a few grams of ammonium nitrate. What we'll see immediately is a change in temperature, meaning the ammonium nitrate will sequester all heat from the water to drive the reaction, therefore reducing the temperature of the water. And then you'll have a constant temperature, which will be very low. And this is the concept of an Icepack. This is how Icepack works. And this is the basis for how we approach these fundamental questions, that there is some heat being generated or consumed, and we use the measurements of these heats to determine the reaction is, what the governing reaction is. As a follow-up to this concept, we could do a flow calorimeter, which is more suited to, say, a landfill environment where you have a pulse of water moving through an aquifer. And one could imagine one could imagine there's a column or some fraction of an aquifer, and there's a valve. We have two valves and a bypass. We could insert ammonium nitrate from this Icepack, and we could allow the flow to go through. You could just put your finger there and you'll experience ambient temperature until we allow the flow to go through the ammonium nitrate. Once it hits ammonium nitrate, all the heat from the water will be consumed, and you'll have extremely cold water coming out. And these are reactions that we could tell by just feeling. So the question arises, what about reactions where you cannot see or you cannot touch? And you need some technique in order to go in and measure these heats. And so this is where the flow absorption calorimeter come in. And just quickly, this is what the flow absorption calorimeter look like. And we usually use about 20 milligrams of, here's our amorphous iron. So calorimeter, 20 milligrams of amorphous iron. And this enables us to compress weeks, months, and years of a reaction into minutes. So we could speed up the process, for example, under a landfill. So experimentally, this is what we have. We have the ability to deliver any solution we want into this column. These wires sticking out are the thermistor, thermistor 1, thermistor 2. We have a space in the column for a sample. Any solution comes in, we could measure the temperature before and after the reaction, data capture, data process. Spits out a curve, and then we interpret the curve. So this is exactly what it looks like, right? All right, let's go through a few thought experiments just to get on the same page of how we approach this. Let's think of this as one particle of amorphous iron, one particle. One could easily surmise that it will contain of positive, negative, and neutral charges. We call these sites. These sites are the only places where a particle could go and sit. So an iron particle, chloride, nitrate, any particle in solution could go sit there. Let's introduce this. Let's say we have a flow stream coming in. So you have groundwater from a landfill going in, hitting this one particle. One could easily see that the cation ions, positively charged, will go to the negative sides. Negative will go to positive sides. Neutral will stay neutral. All right, and these positives could be sodium, potassium, iron, or these chloride, nitrates, arsenate, whatever. So this is a confirmation that the positives will go to the negative sides, negative to positive, etc., etc. So the way how we use these chlorides, nitrates, and sodium, we call them probes. And the concept is this. If we allow chloride, for example, to go to the site, chloride will generate a heat or consume heat, will report to us that heat. That heat correlates to how much site does it see. And it reports back to us. So keep this in mind as I'm moving on. So we sit chloride on the surface from a landfill. Chloride sits on one particle, and then we introduce nitrate. Nitrate will interact with chloride because it wants to share the site that chloride is sitting on. Nitrate will attempt to kick chloride off of the site and occupy it. All right, so we have a site now that is totally nitrate saturation, all chloride left. So coming on to the experiment, this is what we measure. So we have chloride sitting on the surface, nitrate comes along, kicks chloride off, generates a heat. We're able to measure the heat. And so x-axis is time. We have about 0 to 60 minutes. Y-axis is volts. This is what we're measuring. We can convert volts to energy, and we know the amount of heat associated. In this particular experiment, nitrate replaced chloride and was exothermic. It was more favorable for nitrate to be on this side than chloride. If we repeat the experiment and bring chloride right after nitrate, so we have chloride coming in now, it will kick nitrate off and occupy the site. So we have a nitrate saturated site. Chloride replacing nitrate is endothermic, meaning it uses heat from the water to generate enough energy to kick nitrate off. And this is what we call a probe. So we'll probe the site, place nitrate, place chloride, place nitrate, place chloride. It reports to us what it saw on the surface. And we know the type of reaction. Think about this. If area 1 is equal to area 2, area under the curve meaning total energy per reaction. If area 1 is equal to area 2, we could tell what type of reaction occurred. It's a simple 1-for-1 ion exchange. Area 1 equals area 2. Exothermic equals endothermic. And this is most useful in proceeding to understand how does ion interact with solid phase ion. And one of the checks and balances we do is we repeat the experiment over and over, and you can tell is nitrate chloride reporting that the surface is very consistent over a period of time. So it's telling us we saw a number of sites. Each time we go, we saw the same site. Question arises, if iron is in solution, what does it do to the site to enable other contaminants like arsenic and chromate and phosphate to be removed from solution? This question in mind. So dissolve ion adsorption on amorphous ion. This is what we're after. We want to understand how does ion interact with the solid phase and the potential for mobilizing arsenic or any contaminant from solution. So same experiment. Now what we could do is we could introduce ion in the flow stream right after nitrate or chloride. So we have a flow stream. We have ion particles in it, the orange ones. They have ion particles. What they will do is they will go after sodium because they're positively charged. They will try to kick sodium off, and they will report a heat back to us. Kick sodium off, and they will sit on the sites once occupied by sodium. So this is actual data. What we have on the x-axis is time. We have 3 experiments: red experiment, green, and blue experiment. What we did in this case is we pulse the surface with 60 minutes, 140 minutes, and close to 3 hours of iron moving through the aquifer. And we want to see how does it modify the surface and allow that particle to consume other ions in solution. Now, one of the interesting things is, at first, which is new to us, is that iron replacing sodium is endothermic. It took heat from the solution in order to get rid of sodium and occupy the surface. This is what happens. Picture aquifer under landfill, reductive dissolution, iron in solution. It will not leave the aquifer. So one of the concepts is, well, if the aquifer dissolves, iron will just move all the way out. But it shows that doesn't happen. Iron dissolves and immediately reabsorbs. Dissolves, reabsorbs, all the way through the aquifer. And the reason why we're able to surmise this is the reaction goes endothermic. So what does adsorption got to do with it? Once iron sits on the surface, it becomes very energetic and continues the reaction forever. So one could imagine, after years and years, iron will sit there, recreate a new site, dissolve, reabsorb, recreate a new site, and keep building the surface. And this is exactly what we see, and has been confirmed by other researchers. One final note is, if iron adsorbs, what does it do? If we bring nitrate and chloride back into the aquifer, we see that iron created new sites for other contaminants to adsorb. And this is the change in volts here.